it good?
Yeah.
All right. So we were talking about the Dirac theory, and I'd like to just pass out a couple of slides. So this is the picture for discovering the positron, and as I told you before, this is the cloud chamber, and there is a track of particle that's actually given by ionization inside this gas, and there's steel plate in the middle, and because of steel plate, you can see the difference in curvature. Below the plate, curvature is not very much. Above the plate, the track is more curved. That means that the particle must have come from below into this picture. And then looking at which way it is curved, they could tell the charge of the particle. So I should have printed 2 copies, but anyway, I'm going to pass this out. So that's the discovery of the positron. And this one I did print 2 copies. And this is the first ever artificially made antimatter. So what this is actually the daughter of Madame Curie, who is also a Nobel laureate, by the way. And what they did is to send the gamma ray into this photographic plate. And inside the photographic plate, the gamma ray, which is a photon, converted into 1, 2 charged particles that left the track inside this photographic film. And one of them is an electron, the other one is a positron. So this is the first human-made ever antimatter. Here you go. And this one is the discovery in Berkeley. So the Emilio Segre and Owen Chamberlain are Berkeley Nobel laureates, and they actually built this the Bevatron. That's the name of the accelerator up on the hill. This is where currently the advanced light source is at the Lawrence Berkeley National Laboratory. And this is the accelerator for proton. They smash the proton on target. So here's the accelerator. It's the proton coming in about 7 GeV. Smashed it on some target. And out came various particles, but among them, there was an antiproton. And this is the first time the antiproton had been ever observed. And this antiproton has been also fed into a photographic plate. And inside this plate, it hit a proton inside the photographic plate, and the antiproton and proton annihilated with each other. And proton is actually a complicated thing made up of 3 quarks inside. And antiproton is made of the anti-particle counterparts. So they met, and they start to annihilate, but there's actually much more complicated thing going on here, like here creation of additional particles like this. And these things are called pion. The bound state made of up quark and anti-down quark. They are both particles and antiparticles counterpart. So something like that must have happened. And as a result, when antiproton came from the top and hit the proton in the middle, that produced the perennial particles going like outwards. And it looks kind of like a star, so it's called star event. And what is happening here is the proton and antiproton annihilated, and that led to the production of totally different kinds of particles in a pion state. So I'm going to pass this out too. So these things are demonstrations that antiparticles really do exist. And one of you asked the question, so how come that we are living in a universe with only basically matter, but no antimatter? And that is one of the biggest questions in cosmology today. And tomorrow, Bethany is actually giving a discussion section about this idea called baryogenesis. And it's a strange word, baryon. Has to do with the word baryon, which is a collective name given to proton, neutrons, and other particles which are made of 3 quarks, just like I mentioned up there. So these particles are collectively called baryons, and apparently this originates from the Greek word meaning heavy, because the protons and neutrons are much heavier than electrons, for example. And universe seems to have these guys, but not these. So that's the strange thing. So the Dirac theory told us that the particle and antiparticle can be discussed on an equal footing, but for some reason, universe is asymmetric. So the idea is that universe started out with the same amount of baryon and antibaryon. But I briefly mentioned this last week. Something must happen to take one antibaryon and convert it into baryon. Nobody has seen a process like this, but something like this must have happened. And then there is a slight imbalance between the amount of baryon and antibaryon in the universe, and pretty much all of them have annihilated with each other, and what remained in the end is basically 2 out of a billion. So this is the process called the baryogenesis, because without this change between the baryon and antibaryon, the universe would have been empty and you wouldn't be here today. So that's the idea. And so the origin of this shift or reshuffling between baryon and antibaryon is the idea called baryogenesis, following the Bible's Genesis at the very beginning of the Old Testament. So that's the idea called baryogenesis. And Bethany will be briefly talking about this idea tomorrow in discussion section, so you don't want to miss it. Yes?
Why do we assume that there is tons of baryons and antibaryons exist in the first place?
Yeah, so that's something we actually know because of the number of photons in the universe today, which is something like 300 per cubic centimeter. And that is basically cosmic microwave background. So if everything was in a thermal equilibrium early on in the hot Big Bang, then number of the baryon and antibaryon must have been about the same as the number of photons by definition of being in equilibrium. But the number of baryons we know today is something like 10 to the minus times the number of photons. And we know that from many different measurements of the way the universe is today. And that goes back to, for example, the observation of the Big Bang by George Smoot in that department. And so this is something we know also. So compared to these two numbers, what must have happened is that we had sort of the same number of baryons and photons initially, but pretty much all of them have been gone by annihilating with each other, and what remains here is just a small portion of it. So that's the way we understand it. Does that answer your question?
Yes,
Yeah.
kind of, but
Yeah.
it still feels weird why there is tons of, like, when we include the photons, why there are photons and baryons and antibaryons exist at the origin of the universe?
That's an interesting question. So what we think, and this is not proven yet, is that the universe started out with a size something like 10 to the minus 26 centimeters. Entire universe we see today, 13.8 billion light years across, was microscopic at the beginning. And it was a quantum world, actually. The whole universe was quantum. And then it stretched exponentially by a process called inflation. And after inflation is over, it started to slow down in its expansion. And then it started to actually speed up again recently, as recent as 7 billion years ago. And this is what is called dark energy, so permanent discovery. And so the idea is that when the universe was stretching like this exponentially from a microscopic size to macroscopic size, that was caused by the energy of the inflation, and then changed into the thermal bath. So the energy got converted from this inflationary energy to thermal bath. And when energy gets converted to thermal bath, that's the point where equal number of particles and antiparticles have been created. So that's the current paradigm. As I said, it's not proven yet, because nobody has observed the consequences of the inflation itself, but there's something in principle possible. And Lawrence Berkeley National Laboratory is leading an effort called CMB Stage 4 experiment, where they would like to see the consequence of the stretching of the space. And when the universe was getting stretched like crazy from this tiny size to macroscopic size, stretching space, if you think about stretching a rubber sheet or something, if you do it so rapidly, then whole sheet starts to shake. In shaking space is the gravitational wave. So as a consequence of the inflation, there must be still basically vibration of space, gravitational wave, as its consequence. And if you could observe that, in some sense you can say that you have seen inflation. And that's the purpose of this experiment. And LBA was leading that effort today. And so we might know in the near future if this is really the right theory. So right now this is an unproven paradigm, I would say, but we are trying to actually prove this experimentally that way. Okay? Yes, over there.
Why did it slow down and then just suddenly increase? So
No,
like, why did it just start increasing from the
That's another $1 trillion question. So again, this is going totally off track. So the way universe expands is governed by something called the Friedmann equation. Which of course comes from general relativity, but you can actually understand this by simply looking at the Newtonian mechanics. If you think of the universe, which is sort of a spherical as an approximation, and expanding outwards, and thinking about how this edge of the space would move. Of course, it doesn't have to be the edge that goes to the outside. I'm just artificially defining a sphere for the purpose of discussion. Then the equation of motion of this tenth mass is simply given by the m r. Then this is r dot is given by gn m inside this radius r m over r squared. Right? But this is the equation of motion. And as a consequence of this equation of motion, we know the energy has to be conserved. And from measurements, we know that this quantity is very close to zero at least, maybe exactly zero. So if that's the case, then the equation of motion is actually very simple. You just write r dot squared, you cancel n from both sides, and write this as 2gn mr r. And if you think of this mass being the collection of non-relativistic particles, mass inside its radius should be proportional to its volume times the density times the mass density. So you actually put that in here, 8 pi over 3 gn r squared rho. So that gives you this equation that r naught squared of r squared is 8 pi over 3 gn rho. And this is again the mass density. So this is actually exactly the same equation you get from general relativity, namely the Friedmann equation. So what it's telling you is that once you specify how much energy is there in the universe, that tells you how fast it should expand. And normally, if you think of this collection of matter, the density, mass density, has to be something that goes down like 1 over volume. So if you actually take that assumption, this is going down like 1 over volume, then dr r 1/2 is dt. Then you can just go ahead and solve the equation, and I'm making some mistake here. That's right. So then you find 3/2 is proportional to t, so r should go like t to 3/2. So that's the expansion. And if this is the case, when you look at r dot, And if you look at our double dot, you find this is negative. So universe should decelerate. That's the sort of the naive conclusion out of this discussion. And that kind of makes sense. Because if you think of the universe being stretched uniformly, everything inside the universe will pull each other. Gravity only pulls, it doesn't push. So if it's expanding and it's being pulled by mutual gravity, it should break on the expansion and it should decelerate. So it's simple as that. So that's the standard picture. However, what seemed to have happened at the very beginning, and also for some reason now, is that there seems to be an energy density which is constant. And let's come back and talk about what it might mean in a minute. But if you assume this, and looking at that equation, and if this is constant, then I can just take square root of both sides. This is also constant. So R dot is constant times R, which means R is e to the constant t as a solution to this equation. So if there is this kind of constant energy density, and as a solution to this Friedmann equation, you'll find the universe would expand exponentially. And if that's true, if you take second derivative, that's this constant squared times R, which is positive, which means that universe can undergo an accelerated expansion. And that's the idea behind this inflation. That's an accelerating exponential expansion. And the universe seems to be doing the same thing all over again recently, for some reason. So both of them suggest that there could be some constant energy density. So far, so good? So the big question is, what could it be? And short answer is we don't know. That's why these theories are still unproven. But constant energy density means something really crazy. So think of one portion of the universe is constant energy density, then total energy is rho times volume. But because the universe is expanding, let's say it becomes twice as large, then the volume is 8 times larger. So this turns into same constant energy density times 8 times bigger volume. So energy is increasing. It's multiplying. So this is, some people call this the technical term called ultimate free lunch. Energy just keeps multiplying. And you might say, well, that contradicts the conservation law of energy, but there is no conservation law of energy in the universe. If you remember, the Dirac Theory told us energy is conserved because of the invariance under the translation of time. Namely that if there is no origin of time, energy is conserved. And in our daily experience, the origin of time is arbitrary. Of course, we tend to wake up when the sun rises, and we want to sleep when the sun sets down, but it's arbitrary. If you go to a different time zone, of course, the origin of time is different. Hence, energy is conserved, because there is no clear origin of time. But in the case of universe, apparently there was origin of time. universe itself is not constant in time, which means that energy doesn't have to be conserved. So it can multiply too. So it turns out that there's nothing that contradicts with the behavior as far as we can tell. It's crazy. Partly the reason why it's crazy is that if you take the derivative of this, that thermodynamics tells you that du is minus p dv. The fact that u is increasing then means the pressure has to be negative. It's a very strange substance that's apparently filling up the entire universe. That's why we call this dark energy. We don't really know what that is, but apparently we need such a thing to basically push the universe. Gravity only pulls, but to speed it up, something has to push. And that is what is called dark energy, which is a substance which is uniform in space, but with negative pressure. And the candidate for such an object is what is called the vacuum energy. And you know, vacuum should have energy, because when you alter the Hamiltonian field theory, you have the 0-point energy summed over all momentum modes, which is infinite, but we know there is such a contribution to the Hamiltonian. But if you sum this up, that's infinite. What we need to explain the data today is that we need energy density, which is in the unit of energy, something like this. It's a pretty tiny energy. So how come that this infinite 0-point energy for all particle species we know add up to somehow magically to something this tiny is a big mystery, and that is what is called the cosmological constant problem. Namely, that cosmological constant is something that could be there as a constant energy density in the universe, which contributes to the Friedmann equation. Once you accept such a constant in the Friedmann equation, you can explain this accelerated exponential expansion of space, which seems to be indeed what's happening today. We think that's what happened at the beginning of the universe too. But what exactly is the cosmological constant, especially in view of this contribution of 0-point energies from all particle species, is something that's totally not understood. We have no idea. And people are so desperate to the extent that now we think that this may be a pure accident. You know what I mean by this? Is that if this vacuum energy is a little bit bigger, then as the universe starts to expand, initially exponentially, and then start to slow down a little bit. But if you make this vacuum energy maybe 100 times bigger, instead of expansion accelerating after 7 billion years, it starts to accelerate much earlier on, before stuff starts to get collected by the gravitational form of dark matter. That's another unknown thing. So that they start forming stars and galaxies. So if the acceleration starts early, by having too much vacuum energy, then universe starts to get stretched so quickly, there's no time for stars and galaxies to form. Then once again, you wouldn't be here today. So we need dark energy to be small. On the other hand, if the dark energy is too small, namely if it goes negative, then instead of pushing the expansion, it would pull. So expansion would stop, then start to come back down. Then the universe would collapse to a point. Once again, that doesn't leave much time for stars and galaxies to form, and you wouldn't be here either. So it turns out that this constant, which is small, really has to be small and positive so that we could be born in a universe today. So this is actually incredibly fine-tuned. It has to be just right. And out of desperation, we now explain this by saying the following. Well, universe was a trial and error. There were just tons of universes born at the beginning for some reason. Most of them ended up having too large vacuum energy, so it starts to expand exponentially very quickly, and there wouldn't be any intelligent life form. And the other half of the universe had the negative vacuum energy. They will collapse to a point early on. Again, there wouldn't be any intelligent life form. Only when the vacuum energy is just right and small and positive, there's enough time for universe to spend in building stars and galaxies, and hence us. And only that kind of universe would lead to the intelligent life form like ourselves. And so it is only those kind of universes that can be observed by intelligent life form like us. And that's the reason why we think we live in a very special universe. And that whole idea is called anthropic principle. And it also undergoes the name of multiverse, because you need to assume the universe is a trial and error. If there were only one universe, you can't do trial and error. To do trial and error, you need to have tons of universes. And if you talk to some of the string theorists, they might tell you, well, that's kind of expected in string theory. But in some counting, string theory predicts this many universes. Then no wonder some of them end up hitting just right, which would give you the correct amount of dark energy, which would lead to the birth of some intelligent life form. And that's the only kind of universe that can be observed, because other universes would not lead to any intelligent life forms to be observed by somebody living in there. So that's the current best explanation to this. If you buy into this or not, that's up to you. But anyway, so that's the idea. And so it's a very strange universe we live in. And so we talked about why universe has only matter and antimatter today. That originates back from this 1 part in billion difference between them. And in this case, at least you can come up with theories. And Bethany has a paper on this already with me on this. And so she probably can tell you about what her theory is to explain why universe is very asymmetric. And in the case of this exponential expansion, you need this kind of constant energy density as a solution to the Friedmann equation to lead to this exponential expansion. But somehow it needs to be done just right. And we now resort to this idea called anthropic principle. Or multiverse. So if you have this many universes, maybe one of them would do it just right. And the fact that the string theory would lead to this many possible universes is called the landscape. So you have maybe a beautiful landscape of mountains and valleys. And in that landscape, you have multiple local minima. Each local minimum corresponds to a universe of its own. And that's the idea called landscape. And this idea was pioneered by our Raphael Busso in a department. So anyway, so that's all I can tell you right now. Yes, Kate.
So when we talked about the zero-point energy, we know that there is a metric for no, that's not a metric. The energy stress tensor.
Right. That's right. So energy stress tensor in that case would be constant times G mu d.
But if I were to follow the energy stress tensor from the beginning, then how would it change? Like, it is still...
Yeah, so the idea is that energy density of the universe, time. It stays constant for a while, so that the universe could inflate. And inflation ends, and it turns into thermal bath. Then starts to go down. And thermal bath, when everything's relativistic, energy density goes like temperature to the fourth. And temperature goes like one of the size. So this actually goes down to the fourth power of the size of the universe. But as the universe getting expressed and colder and colder, at some point, the matter in the universe becomes non-relativistic. Once it's non-relativistic, energy density should go down like 1 over r cubed, right? This is 1 over volume. So that's how the universe must have actually evolved. And recently, we start to have this constant once again. So that's at least the idea. Okay?
Thank you.
Alessandro?
I have a question about the multiverse. If they come from the fact that at the beginning of time, universe was a quantum mechanics state, does this mean that because we actually did observe our universe, we did measure that, is it like the only universe left?
That's possible too, yeah.
Okay.
And it could be some quantum superposition of different universes.
Still?
Yeah. And so, you know, at this moment, that's all speculation.
Okay,
yeah.
okay. Like, it's like we are observing our universe, so in a way we are measuring it.
But we are part of it.
That's also true, yeah.
So that gives it's a really philosophical question about what is the wave function of the universe.
Yeah.
When the observer is inside, what does it mean to observe it? So that raises all kinds of issues. And so again, there's no sort of consistent, agreed upon description of it.
Yeah. Okay, thank you.
Any other questions? I got totally off the track, but anyway. All right. So back to the Dirac equation. So we talked about the fact that Hamiltonian is C alpha dot E plus MC squared beta. Alpha is a 4x4 matrix. Beta is also 4x4 matrix. So that's the only way we could reproduce the relativistic relationship between energy and momentum. This basically by squaring this Hamiltonian. And we already looked at the solution when momentum vanishes. Because it's a 4x4, obviously there are 4 states. And momentum vanishes, so you don't have this term. You have this mc squared multiplied this matrix, and therefore energy is mc squared, and negative mc squared, another negative mc squared. So that's what we talked about. And we also talked about the fact that this is actually spin 1/2 particle, because Hamiltonian commutes with angular momentum only by adding orbital angular momentum, which is x plus b, and spin angular momentum, which is also given by this matrix sigma, and sigma was just 2 Pauli matrices stacked up in again 4x4 form. And using this expression of sigma, and looking at the sigma z component, 1 minus 1, 1 minus 1, you find the spin of these states to be h over 2, minus h over 2, h over 2, minus h over 2. So this is indeed spin 1/2 particle, that's what we learned. But we had to grapple this issue of the negative energy states, and then we followed Dirac to argue that this must be a fermion. All of the negative energy states are filled already. And then we talk about the hole in those Dirac C, and that actually turned into antimatter. And that had been discovered in the pictures you have seen earlier today. So that was the story we finished up last week. So what we would like to do is that rather than assuming the momentum is zero, namely in the rest frame, we would like to come up with the solutions even when momentum is finite. So we just go ahead and solve this equation, and that's what we're doing in the form of problem 2. So we would like to do that, but before doing so, are there any questions so far? Everything okay? All right. So once momentum is finite, one thing we have to grapple with is how we specify a state. Clearly, momentum is conserved in the absence of any interactions, right? And we're talking about free particle. And P would not commute with X, but there's nothing that depends on X in a Hamiltonian, so this indeed commutes. So momentum is a good label of the states. But as we just talked about, spin doesn't commute with a Hamiltonian. So we can say we have a state with momentum P and spin up. This wouldn't work, because spin is not a conserved quantity. But just like what we talked about in the case of photon, you can define helicity, namely projection of the angular momentum along the spin direction. And if you do this, inside J, of course, you have L and spin. But X cross P is always perpendicular to the momentum. If you dot that together with the momentum, take the inner product, that's automatically zero. So the orbital portion of the angular momentum identically vanishes along the P direction. The only thing that remains is the spin. So this is something you can specify. And normally, we divide this by the size of the momentum, so that the size of this operator is just given by the spin. So this is actually plus minus h/2. And this one you can specify. So instead of saying this is the particle momentum P with spin in z direction, we always talk about whether spin is oriented along the spin at momentum or anti-parallel to the momentum, namely that if particle is moving this way, spin might look like this, or it might look like this. And once you specify this helicity, that does commute with the Hamiltonian because P commutes with it, J commutes with it, so the product commutes with the Hamiltonian too. So this is conserved, and that becomes a good label for the state. So what we are looking for then is the eigenstate of that Dirac Hamiltonian for momentum P with definite helicity, and we would like to come up with a solution like that. Any questions about this argument? Everything good? Okay. Then looking at the Hamiltonian, this can be written in this 2x2 block form, and alpha is sigma sigma, so this is sigma dot P, sigma dot P, and mc squared minus mc squared. And we also would like to be sure that P dot sigma h/2, that's this P dot S, has an eigenstate, and this is P dot sigma dot P 0, 0. So what do you see first is that momentum always comes in this combination of sigma dot P. So to diagonalize this Hamiltonian, it's useful to look at this matrix because this is the only way momentum appears, both in the Hamiltonian and also in the Helicity. So what we do is look at this 2x2 matrix first, sigma dot p. And look at its eigenstate. And to do so, we go to spherical coordinates. Then sigma dot p is given by cosine theta minus cosine theta sine theta e to the minus 95 sine theta e to the 95 times b. So just writing out in terms of this the spherical coordinates. Then you look for the eigenstates chi plus minus, which gives you the eigenvalue plus minus p. P is the length of the momentum vector. And I don't do the algebra here, but the solution is easy to verify. Chi plus is this. And if you just go ahead and multiply this on top of this two-component vector, then you can show that this indeed has an eigenvalue of plus b. And when you look at the other one with a negative eigenvalue, it's given by this. And again, you multiply this, and you have to use a few trigonometric relationships among the cosine and sine, but you can easily show that this has a negative eigenvalue of the sigma dot p. And then you use this basically twice, because there's a 4x4 matrix at the end of the day, to work out the eigenstates of the Hamiltonian in the Helicity. Any questions about this? Okay, good. And once you have done this preparation, then the solutions are easy to work out. And this is what you also verify in a homework problem. So because this chi plus is a two-component vector, if you use it twice, that's a four-component vector. And you can act the Hamiltonian I just erased on top of this and find that it is indeed an eigenstate. And E in here is indeed this relativistic energy of a particle with point momentum P. So this is an eigenstate of the Hamiltonian. And it also is an eigenstate of the Helicity. And this one is, of course, very easy to see because sigma dot p is just sigma. This capital sigma is a 4x4 matrix, but it has the 2x2 sigma dot p up and down. They act on this chi plus and give you the positive eigenvalues. So that is something you can see immediately. Hamiltonian requires a bit of algebra of the square root, but again, that's just the high school algebra, so you can also check explicitly that this is indeed the eigenstate of the Hamiltonian. So that is the solution with a positive energy. With a positive energy. And similarly with a negative velocity, and the expression looks like this. So that's how you can get all of the positive energy solutions to the Dirac equation. Okay, any questions about this? Yes?
Just want to ask how the spinner, because the theta is relating to the P.
Let's see.
Is relevant.
Shall I check one of them then?
No. I mean, could you explain a little about how to understand it geometrically? How does this spinner relating to the spin?
One thing you can say is that this depends on theta over 2. And that's really meant to be spin 1/2. When you think of, for example, the spherical harmonics, YLM, that is basically a function that goes like the Lth power of cosine and sine, right? And that's the case we know for the orbital system. What we need to write is basically write the wave function of spin 1/2. So you would expect that the function would go like a 1/2 power of cosine and sine. And indeed, cosine theta over 2 is 1 minus cosine theta over 2 square root, right? So there is a 1/2 power. So the fact that there is 1/2 in theta for all of these components is the indication that this is indeed spin 1/2 particle. Okay? Does that answer your question?
Yes.
Okay. Any other questions? And of course, the way you work it out is simply just an algebra. So that's how you find the positive energy solution. But of course, there are negative energy solutions too. We need to work them out. And here I need to be a little bit careful. So as we talked about, at the end of the day, we expand psi, which is now meant to be a field instead of wave function, right? We have to switch to the quantum field theory instead of single particle quantum mechanics because we have to fill all of the negative energy states. So then we have to go to the quantum field theory. And you are expanding this, again using the same modes. And u plus p e to the minus ip dot x over h bar. Remember this p dot x is p mu x mu, which is ep minus p dot x in the 4-component notation. And this comes with its own annihilation operator. Same thing for the negative energy. So the positive energy but the negative velocity solution. But then you have to add 2 negative energy solutions. And the notation we use is that instead of e to the minus ipx and take energy to be negative, because we know we're going to talk about negative energy solutions, we anticipated, so instead, we put plus sign here, so that energy is negative in the usual sense, but P mu corresponds to the absence of that negative energy in momentum. Therefore, this P with the flipped sign ends up being the real full momentum of the antiparticle. So if you insist on putting minus IP here, you have to talk about negative energy. But you're going to fill those states anyway. And absence of that state is the antiparticle, that's the hole. And then the form momentum of the hole would be absence of that negative form momentum. Therefore, putting minus sign here already relative to the positive energy solution already anticipates that you flip both energy and momentum already to describe the absence of that being the energy of the hole and momentum of the hole. So we actually put this positive sign for that reason. And we also know that these are holes. So in the expansion of the field operator, you need to actually put dagger here. Namely, this is the creation operator. So what we like to do then is, in the case of the negative energy solutions, instead of solving for H equals Cp C alpha P plus mc squared beta, we are flipping both energy and momentum, which means that we are solving for the eigenstate of this Hamiltonian instead. So that actually has to be done a little bit more carefully. So let me repeat. In comparison to the positive energy solutions, where the displayed wave is e to the minus iet plus ipx over h bar, as we have been always doing in quantum mechanics, negative energy solutions are always interpreted to be already filled in the ground state, and removing that gives you a positive energy hole. So the energy and momentum of the hole is the negative of the energy and momentum of the negative energy state that is already filled. That's why we flip the sign of all the form momenta to anticipate that already. And if you put plus sign here, this P mu ends up being the form momentum, energy and momentum of the antiparticle. And because the vacuum state already has all of those negative energy states filled, the annihilation operator, annihilating negative energy state, is the same thing as creating a hole, namely creating the antiparticle. So instead of having an annihilation operator for the positive energy solutions, you need to use creation operator for the negative energy solutions. And that's exactly the same thing we have done for the Fermi degenerate gas in the piece of metal for the electrons. So there's nothing new there. So that's the idea of doing mode expansion in the of the Dirac field. And once you know that this is actually negative sign instead of positive sign, then Hamiltonian changes, then you can work out again the solutions. And once again, you find two solutions. Or two different velocities. And again, you can verify this just by doing the algebra of the trigonometric functions and square roots by acting these expressions for the matrix form of the Hamiltonian. So in the end, we find four solutions: positive energy solution with a positive helicity, positive energy solution with a negative helicity, negative energy solutions for the positive helicity, negative energy solutions for the negative helicity. And using those, we define the creationization operators. You can verify that they satisfy the usual algebra. So that things like A plus minus B, I have to put H, S, Q, look something like this. And the same thing with B's, and this is, sorry, anti-commutational relation. And delta AES, I forgot. They have to refer to the same velocity. And all the other combinations match. So they have the usual interpretation of being the creation operator and annihilation operator for particles. And A is the creationization operators for particles, and B is the creationization operator of the antiparticles. So that's the mode expansion of the Dirac field now. So we made a jump from single particle quantum mechanics, which Dirac wanted to build, but failed. So we switched to quantum field theory. Now psi is a field, and the field is now an operator, and expanded in operators, and coefficient of the creationization operators are given by the solution to the Dirac equation. And so that idea is exactly the same thing as we have done with the Schrödinger field, which was the first half of the course, and also with the Klein-Gordon field, and also even the photon. In that case, the particle and antiparticle are the same, so there's no distinction between A and B, but nonetheless, it's the same idea. It's always expanded in the linear combination of annihilation operator and creation operator. The only difference is the coefficient is now this 4-dimensional vector in this space of alpha and beta matrices, and otherwise, it's the same idea. Any questions about this? Or in general about Dirac theory? So when I say this silence, I'm not sure if you guys are totally lost and confused, or everything is clear. Which way is it? It's clear? No? So what part is confusing?
It's hard to say which part because I'm pretty confused overall.
Oh.
Maybe like one of the things that I'm not sure about is why do we have for the negative energy solutions? So the field psi, yeah, like why is it linear combination of all these four? Is that something? So that's like so each positive energy solution and the negative energy solutions are all solution to, or eigenstate of Hamiltonian.
Right.
That's why we construct the field.
Yeah, these solutions, yeah, right. Perhaps, maybe reminding you about how the Klein-Gordon and Schrödinger field, that might be helpful. In the case of the non-relativistic Schrödinger field, psi x can be expanded. It's non-relativistic, so it doesn't have 2e. And annihilation operator with a plane wave. So in this case, the field operator was purely annihilation. There's no antiparticle, so it didn't have the creation part of it. And that's how this was expanded. But when you have the Schrödinger field plus chemical potential for fermion, we have to split this into two parts. P less than Pf and P bigger than Pf. And here, you actually use B dagger instead. And here again, we had to switch the sign. If you remember, you have this almost problem that you have this the energy and energy minus nu A dagger A, and this was negative. And you instead define A to be B dagger, A dagger to B. You use the anti-commutation relation to rewrite this with the opposite sign here. So you flip the sign. Absence of negative energy is the presence of the positive energy of the whole. And there was a constant, which is part of the vacuum energy we're totally confused about, so let's not talk about this. So instead of talking about the negative energy, we could talk about positive energy at the expense of going from particles to whole. So it's the same thing here. So above the Fermi momentum, we retain the same annihilation operator here. But below the Fermi momentum, that is supposed to be field, we instead talk about holes, and we have the creation operator instead. So this is the forms we are using over here. Namely, the field is expanded originally in terms of the annihilation operators only. But once you see that they are actually negative energy solutions, you have to do something about it. And something you do is to replace the annihilation operator of the particle by the creation operator of the whole, creation operator of the particle by the annihilation operator for the whole. That would change the sign of the energy, and hence you have the creation operator here instead of annihilation operator. But anticipating that you are going to use energy after the sign flip, it should come with plus I here instead of minus I. So that's the idea of how to do the mode expansion when you have these negative energy solutions. And what we are doing here is exactly the same thing. On the other hand, in a case of time only, we expanded this. I think they were H or C, if I remember correctly. We haven't talked about negative energy solutions. But we did use IP.x for the creation operator. That was the way you could do the mode expansion. So even though this is the case of boson, this is the case of fermion, the expansion itself looks very much the same. You have an annihilation operator with a positive energy plane wave, and creation operator with the negative sign for the plane wave. And that kind of makes sense because this is B dagger instead of B. And if you take complex conjugate of this, they switch the role, and this becomes B times usual plane wave, and A dagger times the flipped plane wave. Either way, you are talking about annihilation operator always accompanied by the plane wave of the usual sign, and creation operator with a plane wave with a flipped sign. And that's common to all of these examples. Does that make it look a little bit more sort of reasonable?
Yeah, the general idea doesn't.
Okay, good, good. I'm glad to hear that. Yes.
Could you re-explain why the normalization is over 2e?
Yeah, that was actually the Lorentz invariant phase space. So if you just have the usual sum of the momentum that's like this one, and if you do Lorentz transformation, then one power of E, which is along the Lorentz boost, changes by gamma, so it's not invariant. But if you divide by energy instead, this combination is invariant in the Lorentz transformation. And that's why it is used, normally used in this form of the phase space integral in the mode expansion. Okay, thank you for the question. Any other questions here? Yes, Jackie.
I'm not understanding why the U and V's dissolutions in Hamiltonian are like basis coefficients, because we didn't really do that in Klein-Gordon, and the Schrodinger field?
Because Schrodinger field had only one component.
Okay.
The Schrodinger field had only one component, so there was nothing that needed to multiply this. In some sense, that what corresponds to U and V was just one. But now we are dealing with this 4x4 matrix for the Dirac Hamiltonian, so its eigenstate will be 4-dimensional vector, and that's why you need to do the expansion, retaining this 4-dimensional structure to it. But you want to make sure that this 4-dimensional thing is actually the eigenstate of the Hamiltonian and eigenstate of the Helicity. So that's why we look for these solutions before doing the mode expansion. Another way of saying is that this psi as a Heisenberg field operator should satisfy the Dirac equation. So you can always expand psi as a linear combination of the solutions of the Dirac equation, because it's linear. And then you introduce those coefficients as creation operators and annihilation operators. That's another way of saying the same thing.
Okay.
If that helps.
I think so, yeah.
Okay, good. Any other questions? Any confusions are welcome? Yes,
I was
okay.
looking into the lecture notes, and then Pablo just raised a question about the 2E. But here, there says that there is a case where the normalization has the value of 0, and I don't understand. We have this is 2E, but this is 0. And
Well, that's the orthogonal to each other because they are, so U dagger plus U minus,
yeah.
they are different, the eigenstates of different helicities,
Yeah.
and that's why they are orthogonal to each other.
Okay.
Just like what you know from the quantum mechanics. If you have if you have a permission operator, and if you have eigenstates with different eigenvalues, they have to be orthogonal to each other.
Yeah, I'm confused about the plus and minus.
Okay.
Thank you.
Any other questions? Okay.
I got a question.
Yes.
I've always read that antimatter kind of goes back in time. I don't know if that's a right interpretation of it.
Yeah, so if you look at this expression, and this p dot x is time in it, right? E minus p dot x. And if you say this is the particle moving forward in time, where the coefficient t be minus I times positive number, this looks like this multiplies minus I times positive number times minus t. So you could say that this looks like a solution that is going backward in time. And Feynman really tried to explain things that way. And he even said things like, oh, now I understand why every electron in the universe has the same mass. Because every electron is actually doing this. If it's going forward in time, that's what the next electron. If it's going backwards in time, that's the positron. So every one of them is part of the same trajectory. So if you observe them in a time slice, this electron and that electron, that electron, that electron is the same particle anyway, so that's why they have the same mass. Well, but if this is the right picture, it really does require you have the same number of electron and positron in the entire universe. That's clearly not the case. So, even though that was an interesting idea, that's not the way we think these days. So there is sometimes this description in especially popular science books that you can view antimatter as a particle moving backwards in time, but we don't think that way, at least these days. So it's just an interesting way of phrasing it, but that's not the way we think about antimatter. Is that okay?
Yeah.
Any other questions? Okay. So one thing we learned from these explicit solutions is that when, again, you think about non-relativist limit, energy of the particle is dominated by the rest energy mc squared, so these things more or less cancel. So roughly speaking, the top two components are particles, and lower components are small. If you go to negative energy solution, which are meant to describe the antiparticle, lower two components are large, and upper two components are small. So we use this word that for positive energy solutions, upper two components are the large components, lower two are small components. For the negative energy solution, this fact was, so these guys downstairs are the large components. And these guys upstairs are the small components. But on the other hand, when you go to super relativistic speed, then the rest energy becomes negligible. Then both E are basically the same thing. So you have almost equally occupied the upper two components and lower two components. So it makes this change from non-relativistic limit, where you have a clear distinction between large and small, to ultra-relativistic limit, where every component are pretty much the same. And that actually is an interesting observation, which leads to some of the things that come up later, but right now that's the observation we made. And this is the point where we talk about one important theorem, two important theorems in relativistic QFT. One of them is spin statistics theorem. Namely that if you have a particle with integer spin, it needs to be a boson. If you have a particle with half odd spin, it has to be a fermion. And what we have just finished talking about for the Dirac theory, which is spin 1/2 and therefore half odd, you have these negative energy solutions, which you have to fill. And for that idea to make sense, it has to be fermion, because once the state is filled, you can't put more particles into that state, and therefore that's the ground state. So in order for that kind of idea to make sense, it really has to be a fermion. So we learn explicitly that spin 1/2 particle has to be fermion. And that's indeed what we know. Electron is spin 1/2, that's a fermion. Proton is spin 1/2, it's a fermion. Neutron is spin 1/2, that's a fermion. That's an experimental fact. And in the case of non-relativistic quantum mechanics, that's something you have to bring in from data. But now we actually derive it from theory. Once you go to relativistic QFT, it's not a choice you can make. Spin 1/2 has to be fermion. Otherwise, you can't deal with this issue of negative energy solutions. It's now a prediction. So if there were yet another spin 1/2 particle we haven't discovered yet, we know ahead of the time it has to be fermion, because that's what Dirac theory tells us. Spin 1/2 has to be fermion. Without relativity, without QFT, whether the particle should be fermion or boson was a choice. You could have assumed there might be a spin 1/2 boson, but in relativistic QFT, that's not allowed. And that's this theorem of spin statistics theorem. In the case of spin integer particles, I didn't show this explicitly because it's just rather technical, but it turns out that when you actually try to see if spin integer particle can be a fermion, it ends up violating causality. And if causality violated, you get into this paradox of killing your grandma and why do you exist today. So we don't want to do that. So the spin integer particle has to be a boson. So relativistic QFT already have seen that it has a bigger predictive power. G factor of spin 1/2 particle has to be 2. That's something we derive, and you're looking at a homework problem 2. In addition, you see the correlation between the spin of the particle and the statistics. They were totally two independent concepts in quantum mechanics, but in relativistic QFT, they are tightly connected. Spin integer is a boson, spin half-odd is a fermion. Okay?
Do we mainly separate like the verification of it being integer and it being boson and fermion just by using the commutator anti-commutation relation?
Oh, that's right. So if you try to use anti-commutation relation for Klein quantum field, you run into problem with causality. If you try to use commutation relation for Dirac field, then you can keep adding more particles to negative energy states, and then you have a problem. So either way, you run into problems. So talking about boson and fermion is the same thing as talking about commutation relation and anti-commutation relation. We established that fact back in the Schrödinger field, where you wrote down the multi-particle wave function. And in the case of the commutation relation, multi-particle wave function was symmetric. In the case of anti-commutation relation among creationization operators, multi-particle wave function was automatically antisymmetric. So whether you use commutation relation or anti-commutation relation, it's the same thing as talking about boson and fermion. And the choice was forced upon us. It was not arbitrary. We couldn't choose either way. We have to take a particular choice for spin integer and spin half-odd. And that's one thing we learned from relativistic QFT. So it's more protective than just the quantum mechanics. So that's one thing. Okay? Any other questions about this? Yes, Alessandro.
Maybe like a very stupid question, but
No
what
question was
happened?
stupid.
Well, we will see. What happened with like for like
Go ahead.
for particles that are like spin like 3/2, 5/2, because they are not described in the Fermi.
That's right.
field,
So,
are they?
so Dirac theory describes only spin 1/2, and there are field theories like Morita-Schwinger
Okay.
field, which describes spin 3/2, for example. And we're not going to discuss it because this kind of field is actually special, and this kind of field appears in quantum field theory only when this is within the theory called supergravity. Gravity has spin 2 graviton, and if we have supersymmetry on top of it, every boson has a fermionic partner whose spin differs by 1/2. So spin 2 graviton is accompanied by gravitino, which is spin 3/2. And that's the only context where we use the Morita-Schwinger field in modern quantum field theory. But such a field does exist, and people do use it, but only for the special purpose of talking about supergravity.
Okay.
Yes?
So it seems like you can derive the Pauli exclusion principle from the spin statistics theorem.
That's right.
But in your argument to like describe the spin statistics theorem, you used the Pauli exclusion principle to explain why you cannot have like too many particles in one state, right?
No, so you could have tried to do this, it's erased. So let's say this is a Dirac field and you have this U and V dagger. And with two different velocities I'm expressing it, and you could have tried to deal with this with a commutation relation, which would mean it's a boson. But then, because B dagger would commute with B dagger in that case, you can keep multiplying these things on top of the graph state. And then you can arbitrarily lower the energies, and then the theory doesn't have a ground state. So every electron in your body would decay into negative energy states, and then everything is unstable. So in order to avoid that, you really have to use anti-commutation relation. And therefore, the Pauli's exclusion principle was a consequence, not an input. And as I always argue, it has to be renamed as a diversity principle, but anyway. Any other questions? Okay, and there's one more theory. And then we finish this off. The other theorem is called CP theorem. namely that if you do 3 operations at once, C is called charge conjugation. I will tell you what that is in a moment. P is parity, and T is time reversal. If you do all 3 things at once, that is always a symmetry of the Hamiltonian. Now, parity is something you know, right? So parity is you change the spatial coordinate to its opposite. And you might have learned of this fact that the parity is actually violated in nuclear beta decay. And that's discovered by C.S. Wu, who was a Berkeley alum. So there's an idea of renaming these buildings as C.S. Wu Hall. Right, so it's not decided yet, but that's an idea. I support that. Parity is actually not a symmetry of nature because of that. And time reversal is you have a motion, and you talk about a reverse motion. And if there's a time reversal symmetry, both motions are allowed in a given system. But it turns out that it's known already that a certain particle called a kaon, neutral kaon, this is made up of anti-strange quark and one-down quark. Very strangely, if you observe neutral kaon for a while, it actually turns into its antiparticle. Very bizarre here, but it is observed experimentally. So ds bar turns into d bar s, and vice versa. And experimentally, the probability of neutral kaon going to anti-kaon has been observed. Probability of going backwards has also been observed, but their probability are different. So time reversal is actually violated. And I put up the reference to the experimental paper on V courses if you're interested in what to look at it. So time reversal is not a symmetry of nature either. Finally, charge conjugation is not a very good name, I have to say. But if you have a particle like electron and particle like positron, charge conjugation swaps it. You swap particle and antiparticle. And this one is not a symmetry either, because the universe has only particles and no antiparticles. So every one of them is actually not a symmetry of nature. But in relativistic quantum field theory, you can prove that if you all of them at once, it is still a symmetry of nature. And that is the CPT theorem. And indeed, when you talk about this time reversal violation, that this probability and the probability going the other way around is different from each other. But in addition to going from here to there, if you do charge conjugation, K naught turns into K naught bar, K naught bar turns into K naught. So going backwards like this, now are interchanged. So if you do time reversal, it goes the other way. But if you do charge conjugation on top of it, then you interchange initial and final states. So you're back to the same process, it turns out. So the probability, of course, is identical. In this case, parity doesn't play much role, but if you have to do time reversal and charge conjugation both at the same time to preserve the probability of this transition, so that's one example of that. So CPT theorem is a theorem of relativistic QFT, which plays a very important role. For example, that tells you that if you have a hydrogen atom, and look at the spectra, as we talked about, and their transitions, then you have an anti-hydrogen atom with anti-proton in the middle and a positron circulating around it. these states could be built experimentally at CERN, and Joe Fajan Senior Department is part of that experiment studying this anti-hydrogen atom. And CPT theorem tells you that energy levels of hydrogen atom and anti-hydrogen atom have to be exactly the same. Their transitions also have to be exactly the same. And they're trying to verify the CPT theorem experimentally by studying the property of anti-hydrogen atom. So that's still ongoing, but to the extent they could test so far, that's indeed the case. So CPT theorem is another important theorem once you go to relativistic QFT, and to the extent that have been tested, that is indeed true experimentally as well. So I stop here. Are there any questions? Okay, so what we're going to do next is that we talk about special cases of the Dirac theory when you have only half the degrees of freedom, called wild fermion, and Majorana fermion, that also shows up in quantum matter physics. We will talk briefly about that. But after that, then we combine everything we have done, namely Dirac theory for electron and the Maxwell theory for the photon. If you put them together, then you have the quantum electrodynamics. Then you develop derivation theory for it, and that's where you can really start computing things which were not possible in quantum mechanics, like the pair creation of particles, pair annihilation of particles, and we looked at a few examples of that, and that will be basically the last subject of the course this semester. Okay.